gluons in the atom's nucleus with beams of electrons from the superconducting accelerator. CBAF has an educational mission as well. The CBAF Science Series features scientists and engineers who are gifted at making their work not only informative but fun. The Science Series is held once a month during the school year in the CBAF Center Auditorium. The presentation is live, spontaneous, and for the most part unrehearsed.
Looks real familiar.
Good evening. Welcome to the second program of the Fall 94 Science Series. This is our 6th season. I'm very pleased tonight to be able to present as our speaker one of my good friends and colleagues, Dr. Michelle Shinn. Dr. Shinn was born in Oklahoma, in Stillwater, when her parents were students at the university, then Oklahoma A&N and now Oklahoma State University. And she grew up there getting interested in science by watching her mother, who was very mechanically inclined, fix everything that broke around the house. Michelle, when she was very young, would get to hold the flashlight, and I imagine when she was older, she got the help. She had lots of questions: why, what for, all that stuff. She never outgrew those questions, and consequently, she became a scientist. After she finished high school, she herself attended Oklahoma State University, getting a bachelor's, master's, and PhD from them in physics. After that, she went to Lawrence Livermore National Laboratory, where she worked on a very large, very high-tech laser project that was basically associated with the Strategic Defense Initiative. And since 1990, she's been an assistant professor at Bryn College, which is a women's college outside of Philadelphia, Pennsylvania. In addition, very recently, Michelle got engaged to be married, and she's looking forward very much to that big event in her life. She's here to talk to us tonight about becoming enlightened about light, or how the use of light, in particular lasers, is involved in everyday experience. Please join me in welcoming Dr. Shinn.
Thank you very much, Beverly. And you'll have to excuse me, I've got a bit of a cold from my fiancé, I'm afraid to say. But God bless him. Anyway, so it's a bit husky, but I hope it'll be understandable. And again, thank you very much, Beverly, for inviting me up here. It's really nice to have all you folks turn out tonight, and you could be watching Chicago Hope or whatever it is. So I'll try to make it worth your while. Seinfeld. Anybody watch Home Improvement? Anyway, so we start off with the obligatory opening slide, just to make sure it's all in focus, and it is. And one thing we like to do is sort of give you a brief outline, and I'll keep putting this back up periodically. What we're going to talk about today is sort of the introductions part. Is really, Beverly helped bring that along, but what I'm going to be doing is talking to you about why I'm a physicist. And in part, why I'm a physicist is this continuous asking why. And one of the things that I became very interested in very young were things about light. Rather than spend a lot of time talking about what light is, we're going to talk about what light does and what makes light useful for you and me. Then we're going to talk about what's special about laser light and what's special about lasers. And then we're going to talk about how lasers and light can be used in several ways. Understanding our environment, understanding our weather, how we can use it in medicine, and how we can use it to entertain us. And there's lots of demonstrations, and I'm probably going to need to use one or two of you to help me out. So don't be shy when I ask for volunteers. So, a quick definition. I'm a physicist, and this is one definition, which is one I rather like. Physics is an attempt to describe, in a very fundamental and penetrating a way as possible, the nature and behavior of the world around us. That's really the core thing, I think, for any scientist. But for physicists, it's trying in this very penetrating way to get to the very basic, the very fundamental things about the world. It's the fact that you're like a 4-year-old. And if you've ever been around a 4-year-old, that 4-year-old always asks, well, why does this happen? Why is that? What's that? And a good scientist always keeps that. There's never any lack of asking why. And the wonderful thing is we get to go and do experiments and figure out why, or at least close in on the answer. A lot of people say, well, isn't physics really hard? You know, normally, I think when anyone finds out I'm a physicist, the first thing they do is they go, oh, wow, you must be really smart. Or they go, doesn't that take a lot of math? Or isn't that really hard? And, well, it's challenging. And it does take a lot of math. But the thing about science, the thing about physics, is it's the challenge. It's a challenge like doing crossword puzzles. It's the challenge like reading a mystery and trying to figure out who done it before you get to the end of the book. That's what we as scientists get to do every day. And so it's new and it's different every day, and that's what makes it really, really intriguing. That's what makes my job so much fun. And one thing that we get to do in particular, since I'm what's called an experimental physicist, is we get to play with toys. So I'm going to invite you into my room here, and we'll play with some toys together. Okay. With light, again, I'm not going to go into a discussion about what light is. Some of you already have some ideas about that. But I'm going to talk about the fundamental properties of light that make it useful for us. One of them is light is transmitted through objects. It's transmitted through the air, or if we take this nice demonstration that Steve Gagnon set up, we can have some lasers right now, and we have lights. You can see the two laser beams, red and green, that are shining through the salt water, and you can see that they're being transmitted. They're being transmitted onto 2 dots onto the table. We're also seeing another phenomenon I'm not going to talk about much. We're seeing scattering. The reason you see the lights is they're being scattered by the salt water. But it's this fact of transmission, of course, that allows us to see one another. And we're going to use that fact much later on in my talk in showing how we can use this in a number of ways. Now, light isn't always transmitted. Sometimes it's stopped by things. It's absorbed, like it's absorbed by this table. Different things can change. Different substances have different absorptions. And to show that to you, we're going to use this demonstration. What I have is I have a small laser, a helium neon laser, going through some water. And as you can see, there's a nice spot on the wall, because that's transmitting. Water, being pretty clear, transmits very well. What happens if I take something which is pretty absorbent, like some black ink? I think, can everyone see the dot on the wall? Great, okay. So we're going to take some black ink, and we're going to pour it in. And look what happens. Wherever the black ink crosses the beam, it starts to absorb it. And if I put a little more in, well, actually what I want to see, what we want to do is stir it up a little bit. Thanks, Stephen. And so now you can see the very clear water is now getting very dark. And what's happened to our laser? It's now being totally absorbed. What happens is that can be very useful for us, having something which absorbs. Now this absorbs everything, right? It's black. But we can have chemicals which selectively absorb materials and absorb the light. And that can be very useful for us also. Or we can use the fact that just naturally some substances that we don't want to know about, don't want to have in our atmosphere, pollutants selectively absorb, and we can look and find out if those pollutants are around or where they're around. So that's the phenomena of absorption. Then there's another phenomena which is known as emission or fluorescence. And for that one, we're going to have to dim the lights. What I have here is laser dye that's used in my lab. And as you can see, it's just sort of an orangish substance. And I'm going to turn an ultraviolet light on it. And what you're going to see is what's going to happen is the light will be absorbed, this bluish ultraviolet light, and it'll be re-emitted. Okay, we ready? Just about? Okay. So see this? So that's the phenomena of fluorescence. Something which really is of one color now shines very brightly another color. And that turns out to be a very useful property for us because we can see it. Something which is sort of invisible, this light, now becomes very visible when it shines on something. Okay, we can have the lights back, please. Thank you. Another really nice feature of light is the fact that nothing moves faster than it. And the fact is it moves very quickly. And we use that, the fact that it moves very, very fast, 186,000 miles per second. And we know that value very accurately. I've just made it up approximately, but we know it accurately. And by knowing that very well, if we know the speed of light, then we can use it to measure distance. And I've given some examples. Certainly, a police officer uses their radar guns, and now they're using laser guns, sort of like this little laser pointer, to capture your speed. And it's hard to lie against that one. But it's also used in a lot of other ways. Builders, when they build a highway, when they build a building, are now using lasers and measuring the time so they can very precisely, to get a distance, and that way they can very precisely lay out a foundation for a building. So little lasers are really used in some very fundamentally useful ways for us. But what is it that makes the laser useful for us? Well, let's take a couple of examples. Here we have a small laser, and this laser in my hand is really a marvel. 10 years ago, something like this didn't exist. This is a diode laser, and handheld. And if you look up on the wall, well, I'll put it over here, you can see we get a nice red dot. Now, the thing that's interesting is, if I take this and I put my finger here, see, the dot is pretty small. And when I put it on the wall, it still stays small. If I take an ordinary light, a light like this flashlight, right? I put it on my hand, and see, I can see it now, but I shine it on the wall, and you can't see a thing. See, even if I move my hand, you can see the beam gets bigger. And that's a phenomenon we all have to deal with. That phenomenon is known as divergence. And so one thing to keep in mind, what makes a laser special is that normal lights diverge very quickly, and laser lights don't diverge very much at all. So that means they can be very precisely aimed and pointed. Also, a little bit of light laser power can go a long way. It can go a long distance with that little bit of laser power.
I'm sorry, that's in my eye.
What? I'm sorry? Oh, wrong. Okay. Let's see. Another feature about lasers is that they're essentially one color. We call this monochromatic. Now, a way to show that to you is we're going to take this ordinary light and we're going to block it just so we have a slit. Then we're going to take some of these glasses, which kindly have CBAF has provided to us. And the nice feature about these glasses is they have what are called transmission gratings, little tiny fine lines, finer than a hair across, inscribed on it. And if I put it into the beam, do you see the rainbow of colors on either side? Can we dim the lights a little more? It seems to be going the wrong way. There we go. Yes, see those? Those color, we call that the spectrum of the light. And as you can see, that white light contains everything from the deep, deep purple blue all the way out to the red orange. On the other hand, if we take the laser and shine it, what do we have? We just have red. So we just have a bunch of regular dots, but there's no color. It's all red. And so that, once again, is another special feature that we can use. Laser light is very selective. It's one color. Okay, you can bring the lights back up. Lasers are really pretty simple to build, believe it or not. It takes a few bits and pieces. But a simple laser, particularly the kind of laser I work on, which are called solid-state lasers, are really pretty simple. They have a lamp, a flash lamp that's used just like the lamp in your camera. If you have a flash strobe on your camera, it's like that lamp. And then a little rod of material, and you put it all housed in a can. And the can has something which reflects lots of light and bounces it around. So it goes back and forth through the laser rod a bunch. And then you have two mirrors. One mirror reflects all the light that hits it. No matter what hits it, it reflects it back. This mirror, on the other hand, only reflects back part of the light, maybe 50%, or maybe only 10%. And so when the rod is excited with the flash lamp, it starts to glow. It emits just the way that laser dye emits. And the light bounces back and forth between the mirrors, and every time it goes to the laser rod, it picks up more energy, until finally it comes shooting out that one mirror. And because the mirrors are very precisely aligned to one another, darn, I keep doing that, and because the mirror is fairly small, that's why the laser beam is very tightly collimated. That's why the laser is not very divergent. And because the mirrors are typically coated to emit only one wavelength, to pass one wavelength, then that's why we get the one color. So, while that's a simple laser, one can have a lot bigger lasers. This is the laser at Lawrence Livermore National Laboratory called NOVA. And that is actually a human being, about 6 feet tall, and that is all laser. So it's a building which is about 3 stories tall and almost as long as a football lawn. Not as long as a football field, but about 150 feet, so about half the size of a football field. So it's really a rather huge laser. So we can also make them very complicated. And this one, as Bev was saying, was used to build little hydrogen explosions, and maybe someday it might be used as a laser fusion source to make energy. There's hopes for that. So lasers can go from the very simple, hold it in your hand, to the very complex. And so this just brings it back to remind you, it doesn't spread out, it doesn't diverge, it's almost completely one color, and it can be very intense. So what can we do with that? Well, one of the things we can do is we can study our environment's air and water. Because these substances, like ozone, nitrous oxide, sulfur dioxide, and water, all have specific absorption bands. Just like we absorb the water here, absorb the light, then we can shine the light a laser which is tuned, in other words, which has the same color as where that absorbs each one of these. And if it absorbs the light, if we don't see the light coming back at us, then we know that species is present. In other words, if we've got a lot of ozone and we shine light that's the color of ozone, so to speak, and if we don't see any light coming back at us, if it doesn't scatter back, then we would say there's lots of ozone present because it's all absorbed. We can make very precise measurements of that. So we can look and figure out what's going on, say, over the North or South Pole with the ozone concentrations. In particular, we can look and see what's going on with pollutants in our atmosphere that are being produced by industry, or maybe isn't being produced by industry. And we can do an actual distribution. So not only can we figure out how much there is, but we can figure out where it is. We can also measure things with the wind, and in very particular, if you're flying in an airplane, we can monitor what's called wind shear. Wind shear is very dangerous for airplanes. If you fly into a wind shear, also called a microburst, it can throw the airplane onto the ground. And by using lasers now, they can see what a radar doesn't see. They can actually see the wind shear and thus warn an aircraft in advance that there's a wind shear and have the plane avoid it. They're actually putting these in now at airports like Dulles National Airport. So that's actually happening. And of course, concentration and distribution of water in the atmosphere is important if you want to understand where rainfall is occurring and not occurring over a long period of time. Another very important thing is what's called photoplankton. We talk about the greenhouse effect, the fact that CO2 is building up in the atmosphere. And we talk about the worries about the rainforests being cut down, because the rainforests do a lot of things like take CO2 out of the atmosphere and put oxygen into the atmosphere. But believe it or not, the biggest source of CO2 gobbling and oxygen emitting is photoplankton, which is in our seas. And if we poison the photoplankton, we do two things. We rob ourselves of that oxygen, and we also starve the animals that feed on photoplankton. So it's very important that we go out and we measure photoplankton concentrations in real time, very rapidly. And we can do that now. And we actually are doing it. Just to show you a schematic. This is a system that's being flown in a helicopter. This is just a schematic. But here's the helicopter, and it puts out 2 laser pulses. And so one laser pulse is in the invisible, called the infrared, and the other one is in the green, so we can see that with our eyes. And as it shoots down into the water, part of it is reflected back off the water, and part of it goes down deeper into the water. And so very quickly, because we run these lasers like 10 times a second, we can determine a bunch of things. We can determine how deep the water is. We can determine the photoplankton that's on the surface. We can also determine the salinity, how much salt is in the water. Often we can determine pollutants in the water, all at one fell swoop. And so that's actually being done. Now, I also told you a little bit about, I mentioned that people are using these to check for the emissions from industries. And here's an example of just how compact they've made this. So this is a system that's being used in Germany. And as you can see, it's just in a van. And so the laser's down in here. And here's the telescope that's used to both transmit the laser beam out into the air and to receive the light that's coming back. And again, 15 years ago, this stuff had to go on a couple of flatbed trailers. It was huge. And now we're able to get it all down into a mobile truck that can be driven around from place to place. So cities in Europe, which are particularly plagued with pollution problems, actually are now employing these to monitor what's going on in their air and to try to clean their air up. Well, that's all kind of big scale, esoteric scale. Well, let's bring it down a little closer to home. Let's consider what can be done in the area of medicine. Right now, lasers are about 30 years old, and very quickly they started using them for some surgical procedures, mainly in the eyes, on your retinas, but now they're actually doing surgical procedures in the body, where they're actually going in and, say, getting rid of stones and things like that we don't want. I talked about the eyes, and you're going to see a videotape in just a moment of eye surgery being done, totally painless, very fast, that corrects your vision. They can also do procedures on the skin. Let's say you have a little birthmark that you want to get rid of, except for the birthmark may be in a place you don't want to have it, like on your face. They can go now and quickly remove the birthmark with a laser. These are called port wine stains. That can all be done. There's a lot of skin cancers that can now be treated with lasers. And also, they can very quickly and without needles determine blood oxygen content. And you might think, well, who cares about that? Well, if you've got a baby that's just born, and you want to make sure that the baby can't tell you, I can't breathe, it might just quit crying or something, but they'd like to be able to measure the blood oxygen very accurately. And they can do that now with lasers. They actually have a system where it actually sends the beam of light through the baby's head. And depending on how much oxygen there is, either lets more light through or less light through. And that's all being done in real time now. So let me give you a few examples of this. What do I mean by no need for eyeglasses? Well, what people are doing now is they're taking a particular kind of laser, and they have the optics, and this is the eyeball. And so what they're doing, and here's the part, what we call the cornea. And the cornea of the eye, of course, is where we have our pigment and where we see through. What happens if, let's say you're nearsighted, like I am. Well, the problem there is that your cornea, your whole eyeball, bulges too much. It's not flat enough. We've got to flatten it out. So what the laser does is it cuts little rings. So it cuts a ring. This outer ring is not too deep. And then the ring that's a little bit closer to the center of the eye is closer and deeper. And it gets deeper still. And then finally, you sort of flatten it out. So what you've done now is you've taken an eyeball which is too curved and made it flatter. This is done now on an experimental basis, although in Europe, they're doing it very routinely. And the United States government, actually the Food and Drug Administration, just last week has given it permission for the next phase of testing. And so on a CBS News broadcast on Friday, they actually showed the procedure. And so I taped it, and I'm going to have you see it real quick. OK, we're ready.
Change your battery in that thing, too.
OK.
Surgery to correct nearsightedness, the operation called radiokeratotomy may already be obsolete. Yesterday, an FDA advisory panel recommended approval for an experimental procedure using a laser to make that correction. Dr. Joseph Del Russo is one of the doctors allowed to perform the operation as part of the study, and he joins us this morning from his New Jersey Eye Center, where he is about to show us how it's done on a patient. Good morning. Thank you very much for being with us this morning.
Good morning, Paul.
We should make it clear that Philip is getting ready for the surgery there. Before we talk about the specifics of what you're going to do today, help us understand this morning what the difference is between radiokeratotomy and this laser surgery which you're about to perform.
Well, let me show you two models. For example, in radiokeratotomy, we're trying to flatten the center of the cornea, and what we do is you make cuts, deep cuts, into the center of the cornea, weaken it, and then the center would tend to drop in and be flatter.
And that's what gives you the better vision when it flattens out?
Yeah, because either the eye is too big or the cornea, the front part of the eye is too curved.
And what do you do? And today, show us on the model what you're going to do?
Today what we're going to do is that we're going to flatten the center of the cornea intentionally by using a light. Actually, it's an ultraviolet light, like something like this here. We'll be flashing ultraviolet light onto the center of the cornea to make it flatter, according to the patient's prescription.
All right. Why don't we let the surgery get underway right now?
Okay, good. Philip, are you ready? Okay. So in actuality, it's rather simple. The computer that we have will determine how many pulses of light is necessary to do the surgery. So Phil, just keep on looking at that blinking red light. We'll start now. You'll hear some sounds, you'll hear some ticking. The ticking, of course, is the pulses of ultraviolet light that are reshaping the center of the cornea. And my nurse here is keeping the
So that's what's going on right there,
light.
folks.
And Phil's pretty well. Philip is a 45-year-old doctor who has other
So now
eyes
we're starting to go down
about 6 months
closer.
ago. And he's had an excellent result from that. And
Is Philip feeling anything right now?
if he can hear you, yes.
No, but is he feeling any of the
Nothing
pulses
at all.
of light?
Nothing at all. A few drops, this surgery is painless. With a few drops of anesthetic, the surface becomes numb. It only treats the surface after that.
It's extraordinary that we're witnessing you doing this live. How long does the whole procedure take?
It takes about 30, 40 seconds probably.
Okay.
And as a matter of fact, we're done for.
Now, did the computer stop the action? You pre-programmed it
Yeah.
in?
So we pre-programmed him. His prescriptions are like a -4 in measurement. And what we do is we put that prescription in the computer, and the computer knows how many pulses are necessary to correct the -4. So it's very much more precise than our PET.
How much more successful is this laser surgery expected to be over radiokeratotomy?
The bottom line is that in the hands of a skilled RK surgeon, patients will be able to achieve 20/40 vision or better only about 65% of the time, 65% of the time, which means that the other 35% have to have a secondary operation to bring them up to snuff, as it were. With the eczema laser, in my experience, and we've done about 600 treatments here at New Jersey Eye Center in Bergenfield, New Jersey, our results are that 95% of patients will achieve 20/40 vision or better.
Wow.
With one treatment, and the other 5% we can retreat again.
Is
So
Philip able to talk yet? Because we only...
Yeah, he's here. He can talk, yes.
Now, Philip, you've had this procedure done on your other eye six months ago, and you're quite a sport to sit through this with us this morning. How successful was the surgery?
Oh, it was wonderful. Before, my vision was 2400, which meant I saw the world almost as an impressionist painting, and I couldn't see the big E on the chart. I told my wife before that the only reason I knew that when I was swimming in a lake that it was a lake is my bathtub couldn't fit more than me.
And did you feel anything at all today? Because you didn't appear to flinch or move at all.
No, there was no feeling at all.
Well,
Totally comfortable.
Well, we really appreciate both of you joining us this morning. It's going to be fascinating to see just how quickly this is available in the rest of the country. The good doctor here this morning is one of the few that the government is allowing to do this in the United States right now, although it's being done in a lot of other countries. Thanks again for your time, and I hope it works just as well as it did with your first eye, Philip.
Thank you very much.
I'm sure it will.
15 and a half minutes after you.
We can shut it off. Okay, can we bring the lights back up, please? Oh, great. Now, can you control the volume? Probably not. No. Okay, we'll have to shut that off. Okay, so you just got to see, but I don't want that either. Let's see. Well, my audio-visual assistant has run off, so I'm now, we can fix that in a hurry. That's what I was thinking, too. There we go. A quick solution. All right, I'm just going to have to shout for a minute. So what you got to see, in your own, you heard it, this new procedure is really revolutionary, and it's all being done with lasers. Rather than going with a knife and cutting through, they're able just to go along and use the laser. There's no need for anesthesia, just some eye drops. And again, this procedure seems to be showing better results than the surgical technique with using a knife. But it still needs to be tested. We're very careful about all this. I mean, this is your eyes you're talking about. But it's very possible that people really won't need to go with contact lenses or with glasses in another, say, 10 years. Another thing which this surgical procedure can do, which the one with a knife can't do, is it can correct farsightedness, which you can't do with radial keratotomy. So stay tuned. Well, getting on to the last part of the talk, we've talked now about the big picture, the world, a little bit smaller picture, us and medicine. And now I want to turn back to even maybe, again, a personal view, although sometimes it isn't, and that's entertainment. Not too many people have probably done this, but maybe some of you have gone to laser light shows. I considered setting one up, but I thought, well, it might not display too well. So I'm going to cheat and just show you a picture that was drawn on a planetarium using a bunch of different lasers. And as you can see, laser light shows now are just not all red or green. You can see you've got the whole spectrum now. And so these can be really very pretty. But beyond just like laser light shows, there's really serious thought being given to now starting to set up home theaters or even larger movie theaters, where instead of having the picture being shined with lights, like we have now with projectors, we'd use lasers instead. That's sort of the big scale. There's also a much smaller scale, and that's the CD player that might be in your home computer, or just the CD player you have in your car or in your house. But first I want to sort of show you what we've got in a generic CD player. So what we're looking at is, here's the disc, and we're looking down through the disc. So imagine we've cut the disc in half, and so we're able to look down onto the parts that make up the CD player. And so what you've got is you have a motor which spins the disc, and then off to the side you have a laser. And so here's the laser down here, and it's actually a diode laser, not unlike this one, but at a different color. It's invisible. It shines through a prism and then through a lens which focuses it down onto the CD player. If it hits the flat part right here, that's called a land, it reflects right back down into, it reflects straight back down, hits the prism again, and then goes in and goes into this detector. And we've got something that's fallen in love with it. On the other hand, if it hits one of these raised area, it doesn't shine back in. It reflects off. And so no light comes back. So depending on whether you hit a raised part or a flat part, you either see light, which is bright, or nothing at all. And we take the sequence of lights and darks and turn them into a signal, which we can then pipe out to our TV screen or to our stereo player. To actually show you what one of these things looks like, I brought a CD player over here, and Steve, if you'd give me a hand. Okay, we're gonna display this for you. Get some light on the subject. Let's see if this is working again. Okay. No, still didn't work. Okay. Don't stare at the screen yet. You'll get seasick. All right. You're a little bright. Okay. So what we're looking down at is, here's where the motor is. And the motor is what spins the CD. And right there is the laser. And there's the optic. There's the lens that focuses the beam much brighter. Thank you. So spindle, and the laser. And you see it shoots up, so it has to shoot up, just like in my picture, onto the CD. So if we turn on the CD, you saw that it jumped it, and see how it's going back and forth? What it's trying to do is it's looking for a CD. And so it's zooming in and zooming out, trying to focus that beam, looking for the CD, and it can't find one yet. So it stops. And then if I tell it, away it goes. It starts spinning. Just one more little quick thing. Has anyone ever thought about how a CD is read? Does anyone know how a CD is read? A CD is read from the inside out. So what happens is the CD turns at a certain speed if we're playing, say, track number 1. But if we go way out to, say, track number 11, because it's now reading way out here, and because it has to go a much longer distance, the CD has to slow down. Did you see how much it slowed down? Let me go from that speed. Let me go back to track number 1. See? It's kind of a neat little thing, something you would not know unless you took the top off your CD. But you better not do it without your parents' permission. Okay, thanks, Steve. Well, that really concludes the talk. I think, hopefully, I've shown you that there's a lot of useful things we can do with light, and in particular, there's a lot of useful things we can do with laser light. The fact that it really involves you in your home now. It's where before, 30 years ago, when I was just a child, lasers were all in the laboratory. Lasers were something that was very esoteric, that scientists used. But now lasers are used by you. And so now hopefully you've got a little better understanding and you can explain it to somebody else. Thank you. I'd like to take any questions if anyone has any questions. Yes. Okay. The question, just to repeat the question, I'm going to try this again. Okay, to repeat the question, what kind of laser is used in a supermarket? Now, you've probably all watched what happens when you scan something with a barcode scanner, when the person at the checkout scan goes bzzz, and the cash register goes beep. Well, that's one of two kinds of lasers. 5 years ago, it was this kind of laser, a helium neon laser. And very fortunately, the folks here at CBAF have a laser, a helium neon, that we can show you the insides. So there's this long tube, and you can see the tube's glowing if you kind of bend down. That's a big, long laser. I mean, here's a little helium neon, and it's pretty big. So they're going away from that now. Instead, when I put it down, we're using those little pin lasers like the one I was showing. Thank you very much. So what's being used in a barcode scanner now is this, and this is called a diode laser, and it runs off a little battery. And so that's what's, good question. So that's another use of a laser. Yes?
You said that they might work on things for a home theater and things.
Mm-hmm.
Are they working on it now? And how long will it take before we will be able to use that?
Okay. The question was, I made a comment when I showed the display of the laser light show that they're actually working on taking multiple lasers and using those in movie theaters. And the question was, when are we going to have that? When can we go to the movies and see that? Or when can we buy a laser TV? Well, right now, it's still very developmental. I've heard estimates of 10 years to 15 years. So, but, by that time, you're not paying, you're going to pay adult fare, and so we can afford it. Yes?
use lasers in treatment of cancer for killing cancer cells, but how do they get past, like, without damaging the outer layer of cells? How do they get inside? They don't have to make any incisions. How are they able to do that without damaging the cells around it or in front of them?
Okay, that's a great question. That involves something I'm very interested in. The question was, if lasers are used in surgery for cancer, to kill cancers, how in the world do they get to the cancerous cells if they're buried down in your body? Well, there's a couple of ways. One is, have you ever seen where they do these, where they've actually taken a little fiber optic with a TV and you can actually go along a blood vessel? Okay, that's called a laparoscopic procedure. So you actually take a little fiber optic and you shine light down it, and then the light that comes back gives you an image on your TV camera. Well, if you can shoot light down that pipe, you can shoot laser light down that pipe. So what they do is they thread a little thin fiber, thinner than your blood vessel, along to where the cancer is, and then they can turn the laser on and kill it. That's one way. The problem is, maybe you're not going to kill just the cancer cells. You might kill some of the normal cells along the way. So what can you do with that? Well, there's a procedure called photodynamic therapy. Now, that's a big word, but what it involves is, you notice how this dye absorbed all the light, right? If I had a different color laser, it might not absorb it. What they do is they inject intravenously, inject a dye into your bloodstream that cancer cells absorb and soak up, and normal tissue doesn't. And they give you this, and so all the cancer cells absorb it. And those cancer cells now are very sensitive to a particular wavelength in the red, essentially this color that I'm going to shine on the ceiling, a little bit redder than that. And when you shine that light on it, even though it's not bright enough to burn you, it's bright enough to activate a chemical reaction that kills the cancer cells. And so since only the cancer cells absorb the dye, they're the only ones that get zapped. And that's now beginning to be used, particularly in bladder cancers. And just a couple of years ago, they did an inoperable, by normal means, brain tumor with photodynamic therapy. I want to get one in the back real fast. Yes?
Does lasers have anything to do with radiation?
The question is, do lasers have anything to do with radiation? Well, the word laser is an acronym, which you may know. It's light amplification by stimulated emission of radiation. But radiation is light. When we talk about radiation, we have a bigger generic term. So that's just any kind of light which is given off in a certain way, we call radiation. What most people call radiation is like X-rays, right? Or gamma rays from radioactive materials. And lasers don't have anything usually to do with that kind of radiation. There's a few special kinds of lasers called X-ray lasers, but they require a laser that's as big as Nova, bigger than this room. So there's nothing, like this laser here doesn't generate damaging radiation, just light radiation. There was a question real quick over here. Yes?
Instead of using radars, they use lasers.
Mm-hmm.
What type of laser?
Okay. The question was, though I made the comment about the fact that the police use a radar more often than not to catch your speed, but now more and more they're turning to lasers. And so the question was, what kind of laser do they use? It's a good question, because you have to be careful. Lasers are bright. And so if the laser is at the wrong wavelength, let's say I'm a police officer and I shine it at Bev, then bam, that light could go into her eyes and it could temporarily blind her and she could swerve off the road and get killed. Not good. So you need a laser that can transmit through the atmosphere but not transmit through the eye. And it turns out there's an infrared wavelength Infrared means longer than the red at about 1,500 nanometers. So 1500 nanometers. And it's made by a laser called erbium YAG. So erbium YAG, that's the best way to say it. And that's the kind of laser they're using. And I don't have a picture with me, but the laser itself is handheld, and it's about that big. It's very accurate. And of course, the nice thing about them too, the accuracy is such that you can pinpoint individual cars. Or if you're running a race, doing a marathon or a triathlon, you can pick up individual people and get very accurate determinations of speeds. So that's what that's good for. Yes? Can you blow something up? Okay, the question is, can you blow something up with a laser? The answer is absolutely. I've got lots of pits in my wall in my lab where we accidentally let the beam loose, and it just makes a loud blast sound and a crack, and you see these sparks come off the wall, and and you yell and shut it off real fast. But to be honest, yes, you know, part of the reason that you can do surgery with lasers is that you can cut and burn very selectively with lasers. And of course, there are possible military uses, although the military uses are not so much like a phaser. It's not like in Star Trek, where you'd zap somebody and they would kind of like blow up. I've been zapped by a laser by accident. I've zapped my hand and it hurts. But the problem is people absorb pretty well. So your skin you might get a real bad sunburn and you might blow some sparks off, but you wouldn't blow up. It turns out that what people do there is they try to blind you. So it's not very pleasant, but if you're blind, you can't shoot anybody. And so that's the main use of lasers in the military, one of the big plans. Let's see, there was a question over here.
Why doesn't these lasers burn?
Okay, the question is, why do these lasers not burn? So I can put my hand in here and I can hold it until you guys go home and I fall asleep. That's an issue called intensity. Okay, let's think for a minute. Intensity. Let's say I have a bulb. Let's say at your house you have a light bulb and it's rated at 50 watts. Okay? And that 50 watts, if I could take all of that 50 watts and put it into a little globe, then I could measure at every point what's called an intensity. And that's the amount of watts per unit area. Now what happens is, if the intensity is very low, in this case milliwatts per square centimeter, nothing happens. But if I raise the intensity to watts per square centimeter, like I have in my laboratory, then will start burning things. And then when I go to millions of watts per square centimeter, which is one of my other lasers, you actually start blowing things apart, little spots, like on my hand. So you need lots of watts per square centimeter.
I think it's getting to be 8 o'clock. I'd like to thank Michelle, and people who have questions for her, come up in front and talk to her.
Right.
The rest of you people may want to leave. But thanks a lot. It was a great, interesting.
Thank you very much. Thank you.
We'll miss you. The right half.
The right half? I don't know. We've only found one that was kind of boring.
How do they measure wind with a laser?
Yes.
Are you going to have anything more for adults besides the 55? I really enjoy it. I don't wait too much. But I'd like to learn more, but of course I'm not